Welcome back to the Deep Dive. Today, we're plunging headfirst into a subject that is, well, absolutely foundational to so much of the modern world, yet often goes unseen. We're talking about the intricate dance of ultrasonic wave propagation. You know, how energy travels through materials in ways that unlock incredible insights from medical diagnostics all the way to ensuring the safety of critical infrastructure.
That's right.
You've given us some fantastic material to explore here, and yeah, we're ready to uncover the hidden mechanics.
Indeed. Understanding how waves move through materials, it's like gaining access to their secret language. It's fundamental to pretty much all ultrasonic testing applications, allowing us to see inside objects without, harming them.
Right.
Our mission today is to, well, demystify these core principles, maybe differentiate the various types of waves, and show you how their interactions with materials become these really powerful tools for discovery. We want to help you grasp the essential nature of ultrasonic phenomena, maybe highlighting some surprising facts and practical applications along the way.
All right, let's level set then, right from the ground up. We all talk about waves, but for our deep dive today, let's quickly re-anchor on the precise characteristics that make them so useful for ultrasonic evaluation. What are those key properties we absolutely need to keep in mind?
Certainly. At its core, a wave is a disturbance, right? It actively conveys energy through a medium, and its behavior depends on both position and time.
Okay.
Crucially, it's not the material itself moving from point A to point B, but the energy that's propagating through it.
Right, the energy transfer.
Exactly. In ultrasonic techniques, we're essentially detecting the displacement of a material point from its equilibrium position, or maybe the electrical signal this generates.
Yeah.
And this disturbance, it has several vital characteristics.
Give us the quick rundown on those, the basics.
Okay, well, we measure its amplitude, A, that's the magnitude of that displacement or signal, essentially, how big the wave is.
Okay, amplitude. Got it.
Then there's frequency, or sometimes we use angular frequency. This tells us how many complete oscillations the wave makes in a unit of time, usually in hertz. Its reciprocal is the period. That's just the time for one single cycle.
Right. Frequency and period.
Then wavelength is the spatial measure, the distance in space between two successive peaks or troughs, Related to this is the wave number, which is basically the spatial frequency, how many waves fit into a given distance.
So these are the fundamental dimensions, like the height, the timing, the length. But where it really gets interesting for ultrasonic testing is the speed, right? How fast that disturbance moves.
Exactly. That brings us to phase velocity, V. This is the speed at which a specific point on the wave, let's say, its maximum amplitude propagates through the material.
Like a ripple peak on water.
Precisely like that, yeah. Imagine a peak on a ripple. The phase velocity is how fast that single peak travels. It's calculated as wavelength divided by period or angular frequency divided by wave number. It's the speed of a single, let's say, infinitely long, perfectly shaped wave. But okay, in the real world, especially with ultrasonic instruments, we're rarely dealing with those ideal, perfect, infinitely long sine waves, are we? We're typically sending out short bursts of energy, right? Pulses.
You've hit on a critical distinction there, yeah. While a simple sine wave is our, mathematical building block, most ultrasonic waves used in practice, particularly in non-destructive testing, are actually pulse forms.
Pulse forms, okay.
These are finite bursts of energy, not continuously repeating oscillations.
And how does that change things? Like, is there a different way to think about their speed?
Absolutely. We distinguish between periodic waves, which, repeat themselves indefinitely, and non-periodic waves, or pulses, which have a finite length. These pulses are what we use to get those clear, distinct echoes back in testing.
Makes sense. And for these pulses, the concept of phase velocity versus group velocity becomes really crucial. While an individual sine wave component of that pulse travels at its phase velocity, the pulse itself, which is really a group of these individual sine waves, travels at what we call the group velocity.
Ah,
Yeah.
so it's the speed of the entire packet of energy, not just one point on one way.
Exactly, the speed of the envelope, if you like.
And I've heard that these pulses can actually change their shape as they travel through a material. That sounds like it could cause some serious headaches for, accurate measurement.
It certainly can. In ideal, perfectly linear elastic materials, phase and group velocities are identical. Simple.
Okay.
But in real-world materials, this relationship is often nonlinear. It gets more complicated.
Meaning
Each individual sine wave that makes up the pulse travels at a slightly different phase speed.
Ah.
And this phenomenon is called dispersion. When the pulse's shape changes as it propagates because its constituent frequencies travel at different speeds,
Yeah.
well, the material is said to be dispersive.
Right, dispersion, so that different frequencies spread out.
Exactly. And it's a crucial concept because it means the signal you receive might not look exactly like the one you send.
Hmm.
Accounting for that is absolutely essential for accurate defect sizing or material characterization. Imagine trying to read a message where the letters start rearranging themselves mid-flight. That's kind of the challenge dispersion presents.
That's truly fascinating. The very envelope of the wave can transform. Okay, so we have these energetic pulses moving through a material, but what happens when these unseen forces encounter something else, like an internal flaw, or maybe just the edge of the material itself? This must be the very core of how ultrasonic testing actually works, right?
Exactly. This is where waves become incredibly useful for, well, seeing inside materials. When a wave encounters a boundary, several things can happen. If that boundary is large relative to the incident wave's wavelength, the wave is reflected, much like, light off a mirror.
Okay, reflection.
And the angle of reflection will equal the angle of incidence. Simple geometry. However, if the boundary is much smaller than the wavelength, say, a tiny inclusion or perhaps a grain boundary inside the metal, the wave is scattered.
Scattered. So not just bouncing back.
No, scattering means some energy is reflected sort of in all directions, but a major portion usually passes through.
So by detecting these reflected signals, or maybe the scattered ones, we can essentially map out what's inside a material, like finding cracks or voids.
Precisely. In ultrasonic testing, detecting these echoes and analyzing their energy, their arrival time, their direction, that's how we pinpoint internal discontinuities. We can figure out their size, even their orientation sometimes.
Okay. And what about crossing from one material to another, like steel to water?
Right. Then there's refraction. If the boundary separates two different materials, some energy is reflected, sure, but a significant portion is also transmitted into the second material. But it usually changes direction as it crosses. That's refraction. And the angle of transmission, it depends on the incident angle and the phase velocities in both materials.
Got it. Reflection, scattering, refraction, anything else?
Yes, one more key thing, attenuation. As a wave propagates, through any real material, inelastic mechanisms gradually remove energy from it. It gets weaker.
It loses steam, basically.
Pretty much, yeah. This process is called attenuation. Eventually, the wave's energy decreases until it's too weak to detect. This is measured by an attenuation coefficient, and it's a vital indicator of a material's internal structure. High attenuation might mean lots of scattering, maybe porosity or other microstructural changes. It tells you how much energy is being lost along the travel path.
So attenuation tells us not just if a wave hits something big, but also how much energy it lost just traveling through the material itself. That's another layer of information.
Exactly. It adds to the picture.
Now, it sounds like waves aren't just one size fits all. You mentioned pulses versus continuous waves, but are there different sort of personalities of waves depending on how they actually move through a material?
Oh, absolutely. In 3 dimensions, we generally categorize waves by how their particles vibrate relative to the direction the wave itself is traveling. Think of plane waves first. Imagine like a flat sheet of disturbance moving through space.
Right.
Within these plane waves, we have longitudinal waves. Here, the particle disturbance vibrates parallel to the direction of propagation.
Like sound in air or pushing a slinky.
Exactly like pushing a slinky.
Yeah.
It compresses and expands along the direction it's moving. These cause local volume changes, compression, and rarefaction, sometimes called dilational or irrotational waves.
Okay, longitudinal. And the other main type of plane wave?
That would be transverse waves. Here, the particle disturbance vibrates perpendicular to the direction of wave propagation.
Like shaking a rope up and down.
Perfect analogy. Shaking a rope up and down, and the wave travels horizontally along it. These are also known as shear waves, or sometimes equivoluminal waves, because, importantly, they do not cause local volume changes, just shearing motion.
Longitudinal and transverse. Got it. Any other types besides these plane waves?
Well, distinct from plane waves, we also have spherical waves. These are disturbances that radiate outwards from, like, a point source. Yeah. The phase is the same on any spherical surface, expanding outwards.
Okay. So far, we're talking about waves traveling through the bulk of a material. But what about waves that are almost, stuck to the surface? I've heard those are particularly useful in certain types of inspection.
They really are. These are surface waves, and as the name suggests, they're constrained to propagate along the surface of a solid or maybe a liquid. Their energy is concentrated very near the surface, typically only about 1 wavelength deep.
So they don't penetrate far.
Generally, no. A really prominent type is the Rayleigh wave. With these, the particles on the surface move in a kind of elliptical path as the wave passes. Think of a buoy bobbing on water. It goes up and down, but also slightly back and forth.
Huh. Elliptical motion. Interesting.
Yeah, and what's truly fascinating about Rayleigh waves is a couple of things. Their phase speed is actually slower than the transverse body waves in the same material.
Slower.
Okay. And critically, their attenuation increases with frequency, which means higher frequency Rayleigh waves are confined even closer to the surface.
Wait a second. That's a huge insight. If higher frequencies stay shallower, does that mean we can effectively tune our inspection depth just by adjusting the frequency of the Rayleigh wave we send in?
Precisely. That's exactly what it means. By varying the frequency of the surface wave used in an ultrasonic test, we can probe material properties at different depths, right near the surface.
Wow.
It gives us this powerful, non-invasive acoustic microscope for looking at surfaces. We can look for very fine surface cracks with high frequency, or maybe slightly deeper for subsurface defects using a lower frequency, just by changing a setting on the instrument.
That's incredibly powerful, a tunable depth probe. Now, what happens if a solid surface carrying one of these Rayleigh waves comes into contact with a fluid, like, say, water, during an immersion test? Does that unique surface behavior change?
It does indeed.
Hmm.
That brings us to what are called leaky Rayleigh waves. Yeah, leaky. If a solid surface with a Rayleigh wave is in contact with a fluid, the wave's vertical displacements, that up and down motion, can actually couple energy into the fluid. It sort of pushes on the fluid. This leaks energy away from the surface wave into the fluid, usually as an acoustic wave traveling off at a specific angle called the Rayleigh angle.
So the wave loses energy into the water.
Exactly. And this leaking of energy can actually be detected and analyzed, giving us even more information about the surface and the interface between the solid and the fluid. In fact, there's some interesting physics. If an incident acoustic beam from the fluid strikes that solid interface at this specific Rayleigh angle, the reflected field can show odd behavior, including a null zone, where there's a sort of phase cancellation, and energy gets concentrated in other directions.
Fascinating. Are there other types of surface waves, then, that maybe behave even more uniquely, perhaps ones that don't leak energy into a fluid?
Yes, there are. Think back to our transverse waves, the ones vibrating perpendicular to travel direction. If the particle displacements are restricted only to be horizontal, so parallel to the surface, but still perpendicular to the propagation direction.
Right, side-to-side shaking along the surface.
Exactly. You get transverse horizontal waves. They're often known as love waves, particularly in geophysics, but the principle applies. What's unique about them is that they don't couple strongly with acoustic waves in a fluid, because there are no significant vertical displacements at the surface. Nothing really pushing the fluid up and down.
Ah, so they don't leak.
Right. This means they can propagate along a free surface or even through a plate in their fundamental mode, often without dispersion, which offers a different set of opportunities for specific types of surface inspection where fluid coupling might be an issue or undesirable.
So the way the wave vibrates, where it travels, even what it hits,
Yeah.
it all dictates its behavior. But the material itself, that must play a huge role, right? Does it matter if a material is uniform in all directions or if it has a kind of grain to it, especially when we're trying to test it ultrasonically?
Oh, absolutely. A massive role. That brings us neatly to the distinction between isotropic versus anisotropic materials.
Okay.
Most common engineering metals and alloys, steel, aluminum, things like that, are generally considered elastically isotropic,
Isotropic meaning?
meaning their elastic properties are the same in all directions. This is usually because they're made up of many tiny crystals or grains that are randomly oriented. So on average, it behaves the same way no matter which way you push or pull it or send a wave through it.
And how do waves behave in isotropic materials?
In these materials, it's relatively straightforward. Only two distinct types of body waves can propagate. A longitudinal wave, which is always faster, and a transverse wave. Nice and simple.
But I imagine that's not the case for some of the advanced materials we use now, like composites in aerospace or something.
Precisely. Modern materials like advanced composites or even specially prepared single crystal alloys, maybe for turbine blades, they're often designed specifically to be anisotropic.
Meaning their properties do depend on direction.
Exactly. Their elastic properties vary significantly with direction. They essentially have a grain or preferred orientation at the microstructural or even atomic level.
Okay, so how does that affect the waves? Does it get messy?
It gets much more complex, yes. In these anisotropic materials, 3 distinct wave modes can propagate through the bulk, not just 2. And each one has a different phase speed and a distinct direction of particle vibration relative to the propagation direction. We often describe these as quasi-longitudinal and quasi-transverse modes because the vibration isn't perfectly parallel or perpendicular anymore.
3 modes instead of 2. That sounds incredibly complex for ultrasonic testing. Are there particular challenges this anisotropy introduces for inspectors trying to find flaws?
There's a major one, yeah. A really intriguing effect of anisotropy on waves propagation is that the group velocity, remember, the speed of the wave pulse itself?
The energy packet.
Right. That group velocity can actually travel in a different direction than the wave's direction of propagation, meaning the direction the phase fronts are moving. It's called beam skew, or energy flux deviation.
Whoa, wait. The energy goes sideways compared to where the wave seems to be pointing?
Sort of, yeah. It can lead to really unexpected reflections.
Yeah.
For example, you might be testing a cylindrical composite component, aiming your transducer straight down the axis.
Right.
But because of anisotropy, the actual energy beam might veer off course and hit a sidewall, giving you an echo that seems to come from the wrong place entirely.
Wow, that would be confusing.
It is. This complexity makes ultrasonic testing of such materials particularly challenging. It requires specialized knowledge, often different probe angles, careful calibration, but it's also incredibly revealing about the material's internal structure and orientation if you know how to interpret it.
It's almost mind-boggling how much information these invisible disturbances carry and how much the material directs them. Okay, let's go back to waves hitting boundaries for a moment, but get a bit more specific about the rules. What governs exactly how they reflect and refract? And how do we use that to interpret the echoes we see in ultrasonic systems?
Right. This is where fundamental physics really shapes our understanding and our techniques. When a plane wave hits a, let's say, free, flat boundary in an isotropic material, a crucial principle emerges: Snell's law.
Ah, Snell's law. I remember that from light optics. Same idea here.
Very much the same core idea, yeah. It dictates that the phase of each plane wave the incident one, and any reflected or refracted ones must be equal all along the boundary for all time.
What does that mean practically?
Well, it means that the waves have to keep step along the boundary. The component of their phase velocity parallel to the boundary must be equal for all the waves involved. And this mathematical requirement directly links the angles of incidence, reflection, and refraction to the respective wave speeds of the materials.
Okay, so Snell's law relates the angles and speeds. Now, you mentioned earlier that when a wave hits a boundary, it can sometimes split into different types. I've heard that called mode conversion in ultrasonic applications. How does that fit in?
It's a critical concept, yeah.
Yeah.
And directly related to satisfying those boundary conditions dictated by Snell's law in physics. When an incident longitudinal wave, for example, hits a boundary, it typically doesn't just produce a reflected longitudinal wave.
Okay.
Instead, to satisfy the conditions at the boundary, like zero stress on a free surface, it often has to produce both a reflected longitudinal wave and a reflected transverse wave.
Ah, so the incoming energy splits into 2 different types of outgoing waves.
Precisely. That transformation of wave type upon reflection or refraction is exactly what we call mode conversion. The incident energy is effectively partitioned between these different wave modes, each traveling off at its own speed and angle according to Snell's law.
Is that always true? Like for all wave types hitting a boundary, does a transverse wave also split into different modes?
No, it actually varies considerably depending on the type of transverse wave, and this variability is highly useful for specific inspection techniques.
How so?
Well, remember the transverse horizontal mode, the one vibrating parallel to the surface?
Yeah, the love wave type.
Right. If that wave hits a free boundary, it's much simpler. It is reflected only as a transverse horizontal wave.
No mode conversion.
No mode conversion occurs. And the amplitude of the reflected wave equals the incident wave, assuming no losses. This happens because its displacements are purely parallel to the surface, so it doesn't interact in the same complex way with the boundary conditions that require coupling to other modes or fluids.
Okay, that's simpler. So what about the other type of transverse wave, the transverse vertical mode, the one vibrating perpendicular to the surface but still perpendicular to propagation? Does that also behave differently?
That one is actually the most complex and offers some really profound insights, especially for surface analysis.
Okay.
Here, we encounter something called a critical angle. There's a specific angle of incidence for this transverse vertical wave. If the wave hits the boundary at an angle less than this critical angle, you get both reflected longitudinal and reflected transverse vertical waves. So again, mode conversion happens. Pretty standard.
Okay, below the critical angle, it splits. What happens above it?
But And here's where it gets really unique if the incident angle is greater than that critical angle. A reflected longitudinal wave cannot occur. The physics, Snell's law, just doesn't allow it.
So no longitudinal wave comes back.
Right. Instead, to satisfy the boundary conditions, what happens is a reflected transverse vertical wave appears along with a surface wave.
Wait, a surface wave just pops into existence. So by hitting the boundary at a specific angle with a bulk wave, we can actually generate a surface wave.
Exactly. It's quite remarkable. This reflected surface wave isn't quite the same as a classical Rayleigh wave generated directly. It has some distinct properties, like a phase velocity that can vary with the angle of incidence above critical. But its amplitude still decays exponentially away from the surface, confining its energy there. This critical angle isn't just a boundary, it's like a gateway. Beyond it, the incident energy transforms in this unique way, giving rise to these surface waves.
And why is that useful?
Well, this seemingly complex shift is actually a powerful phenomenon. It allows us to specifically generate and manipulate surface waves by controlling the angle of an incident bulk wave. This gives us another tool to probe surface characteristics with incredible precision, acting almost like an acoustic microscope for material interfaces, revealing flaws or properties that might otherwise be invisible.
Wow. Okay, so from just a simple disturbance carrying energy, we've really unpacked how these waves behave, how they can morph, and how they reveal secrets about materials based on their frequency, the material's own internal properties, isotropic or anisotropic, and even the precise angle at which they encounter a surface. It's like these waves have an entire complex language of their own that we can learn to read with ultrasonic testing.
Precisely.
Hmm.
That's a great way to put it. What we've discussed today, from the fundamental definitions in the behavior of pulses, understanding dispersion, to the different wave types like longitudinal, transverse, Rayleigh waves, and their really intricate interactions with boundaries, mode conversion, critical angles, and varying material structures. All of that is truly the bedrock for so many advanced ultrasonic applications.
Yeah.
Understanding these propagation phenomena is absolutely essential for anyone delving into non-destructive evaluation or material science, really, because it dictates how we generate signals, how we receive them back, and ultimately how we interpret them to truly understand the hidden condition of the world around us.
And it really highlights the incredible complexity and, frankly, the insight we can gain from something we can't even see or hear with our bare senses. It's all invisible physics doing the work. So what does this all mean for you, listening in? Well, next time you hear about a bridge being inspected for hidden cracks, or maybe a medical scan being performed to visualize internal organs using ultrasound, you'll know that it's all built upon these fundamental, often invisible principles of wave propagation we've just explored. It's not magic, it's physics.
And maybe consider this as a final thought. If just changing the frequency of an ultrasonic wave can allow us to effectively probe different depths within a material, as we discussed with Rayleigh waves, what other hidden layers of information might we uncover by precisely controlling these invisible waves in new and even more inventive ways? Thinking about tailoring waveforms, exploiting anisotropy, using those critical angles, the surface, quite literally, has only just been scratched.